Can everybody hear? Can everybody hear me up there? We're good? All right. So last time we left off with NP-completeness. We're still keeping up with these NP-completeness problems and NP-completeness proofs. So in terms of the Chomsky hierarchy, we're in this region here, P and NP, non-deterministic polynomial time and deterministic polynomial time, exploring in greater detail those two regions. And just to recall the definitions, we said a problem is NP-complete if it's NP-hard and it itself is an NP, that problem. NP-hard simply means everything in NP reduces to that problem in polynomial time. That's usually the harder part to prove, this reduction of all of NP to that problem in polynomial time. So in more detail, there is deterministic polynomial time, P, non-deterministic polynomial time, and the complement of the problems in NP are the co-NP problems, and that's what the region looks like. And we're kind of halfway through kind of studying these problems, their interrelationships, reductions among these problems, and so on. So it's all about reductions of problems to other problems, same as before, except now we watch the clock. The reductions better be efficient, and that's what we're focused on. So if we can reduce a problem to another problem efficiently, if that other problem is solved in a polynomial time algorithm, then the first problem can be solved in polynomial time as well. So if any one of the NP-complete problems is in P, they all are, and therefore P is equal to NP. And that's still an open problem. So we proved Cook's theorem that showed that satisfiability is NP-complete, and then we proved a more restricted version of satisfiability 3-sat, where every clause in the formula, in the Boolean formula, can have at most 3 literals, variables or negations of variables. And when that happens, it remains NP-complete because you can always transform an arbitrary formula in conjunctive normal form to 3-sat, a formula where every clause has at most 3 literals. And the proof is pretty straightforward. Long clauses become a series of short clauses. How many? At most a linear number in the length of the longer clause. So it's a polynomial time transformation. And of course, you got to do this for every long clause. And then 3-sat becomes NP-complete as well, because all of NP reduces to sat, satisfiability. That's Cook's theorem. Here we showed that satisfiability reduces to 3-sat. So by composing these two transformations, all of NP transforms to 3-sat. How many are good with this? Okay, any questions about that? That's kind of in 2 minutes what we've done the last couple of lectures. So we mentioned that 1-sat is relatively easy. You need to look for a variable and its negation, and the formula is satisfiable if and only if it doesn't contain a variable and its negation. You can do that in linear time or close to linear time. 2-sat, we left as extra credit to show whether 2-sat is polynomial time solvable. We insinuated that it is polynomial time solvable, and for extra credit, come up with an algorithm to solve 3-sat. So, 2-sat. So for 3-sat, that's where complexity explodes, right? 1-sat is trivial, 2-sat is relatively easy to solve in polynomial time. 3-sat is where NP-completeness rears its ugly head and makes complexity explode at that point. So then we gave a bunch of classical problems that are all NP-complete. We said right after the heels of Cook's theorem, Richard Karp noticed that there's nothing special about satisfiability that it's NP-complete. Dozens and dozens of other problems acquire that status very quickly. They're all NP-complete. They're all as efficient or inefficient as one another. They're all bundled up in this class of NP-complete problems. So Cook stumbled upon satisfiability as the first one of those, but there's nothing special about that. It could have been any one of the other ones that was noticed first, and then the others would quickly follow. But historically, something had to be proven first, NP-complete, and historically, satisfiability was it. So the clique problem, given a graph and an integer k, is there a subgraph, complete subgraph of size k, a k clique? So we mentioned you can look for cliques, but in general, if the clique is not painted, like this clique here of size 6, this clique here of size 5, here if I say is there a clique of size 4 or 5 or 6, it's not so obvious, because you have to look at all subsets, and that's potentially exponential time if you do it brute force, right? So other problems are NP-complete, set cover, given a universe of objects and a bunch of subsets. Is there a collection of subsets k of them that together cover the entire universe of objects. NP-complete. Again, these are all parts of Karp's paper. He showed that about 20 problems or so, 21 problems are all NP-complete, and I'm just showing you a sampling of a few of them. Hamiltonian cycle. Given a graph, is there a path through the graph that covers every node exactly once? Not every edge exactly once. Some edges can remain uncovered or untraversed by this path. But you got to traverse every node at least once. So there's a Hamiltonian path in red through this larger graph where these dotted edges are not used in the path. Only the red edges are. Okay, so graph coloring. I give you a graph and you say, tell me if it's colorable using, say, 3 colors where no two nodes that have an edge between them share the same color. So here's some examples of 3 colorings of graph. No two nodes share a color if they have an edge in between them. And there's entire books on each and every one of those problems. So here are just a few books on graph coloring, but all these other problems have entire books on them. You can study them for a lifetime, each and every one, come up with heuristics and test them ad nauseum, optimize them, try to come up with quick and dirty solutions in polynomial time. But none of these problems, as far as we know yet, are solvable in polynomial time if you want an exact solution, because they're all NP-complete. Another classical problem, partition. I give you a bunch of integers, and you tell me if there's a way to divide that set into 2 subsets such that both subsets have the same sum. Sounds innocent enough, right? What can be hard about that? Well, looking at all combinations is all, it's not just quadratic or cubic number of combinations, it's exponential number of combinations. So brute force, it will take exponential time with a pretty straightforward algorithm, but exponential time, very inefficient algorithm. We don't know how to do this efficiently. Again, it's NP-complete. The knapsack problem is a similar problem, but here you have a bunch of objects and each one has 2 constraints, a dollar amount or a cost more generally, and also a weight. And then you have a backpack that can carry at most, say, n pounds or n kilograms, and you want to put as many of these objects in the knapsack to maximize the total cost of all these objects, the total value of all these objects. So which objects would you put in this knapsack to maximize the total value, given that you can only put 15 kilograms at most, and each one has its own weight and cost value, separate from all the others, and they're all independent. So this problem is very ubiquitous. It comes up in all sorts of applications. Again, entire books are written about this. So for example, did anybody encounter this problem in real life? When do you encounter this problem, by the way? Just to see if you can calibrate this abstract description against real life experience. Yeah, if you're going on a trip and you have a small backpack, or if you're going on a plane and the suitcase has a 50-pound limit, right? And you're over the weight limit. So you have to pick and choose. And you say, oh, sorry, sometimes airlines are kind of strict about that. And they say, okay, you have to get rid of some of the objects, some of the weight in your suitcase to get it below 50 pounds, and you may have to leave some stuff behind, unless you want to pay hundreds of dollars of extra weight costs for the suitcase, which is not usually worth it. So which objects do you take with you and which do you leave behind? That's a tough problem right there at the airport. How many have encountered this kind of situation before? It happens. So obviously you don't want to jettison your jewelry or your cash or your laptop. Those are expensive items and they're relatively low weight. You want to maybe jettison your T-shirts or your water bottles or whatever it is. It's not very valuable but weighs a lot. Those go first, right? Those you can leave behind. Or let's say your house is burning down and you can only go in there once. You only have a few minutes before it burns down completely, fire is out of control, and you want to save some of your belongings. And you can only carry, say, 50 pounds with you, and you only have one trip into the house and out again. So what do you grab out of the house that will maximize your value, given that it has to be no more than 50 pounds, otherwise you couldn't carry it. So again, exactly this problem. Right? It comes up all the time. So in the case of a burning house, you may want to take your jewelry, your cash, your laptop or whatever, but you certainly don't want to take big water bottles out or things that are easily replaceable that weigh a lot but aren't worth very much. And by the way, cost here is not necessarily dollars and cents. When I say cost, it's a generalized quantity. So the cost can be sentimental value, right? That could be the worth to you. So some person may not care about their laptop so much, but they may have a black and white family photo from a century ago of their great-grandparents, and that's worth a lot more than their laptop to them. That's irreplaceable. So they may want to grab that. So just saying cost doesn't mean dollars and cents necessarily. Whatever matters to you is the value of these relative items. Okay. So NP-complete. So now you know why it's so hard to decide what to leave behind at the airport when they tell you you're over the weight limit. Technically, it's an intractable problem. We don't know how to solve it exactly. So don't feel so bad next time. Other problems, bin packing. You have a bunch of bins, they're all equal sized, and you want to minimize the total number of bins necessary to accommodate some large number of objects. So this is a one-dimensional version. Here the bins are all, say, 80 units high, and all these objects have lengths, and you want to minimize the number of bins. This example here uses 19 bins here across, and whether it can use only 18 bins by rearrangement of the items to take more advantage of the empty spaces there, it's not clear, right? And in general, it's NP-complete. That's just a one-dimensional version. But this problem comes in two-dimensional versions, three-dimensional versions, which is even harder, right? In real life, and again, you need to solve this all the time. When did you need to solve this in real life, in your own experiences? Yeah, you want to put away in storage some stuff and minimize the number of boxes it takes. Or if you're moving your apartment or house and you want to minimize the number of boxes that all your stuff will go into so that you can pick a smaller truck or it'll all fit aboard your car or your SUV or whatever. Same problem. You want to minimize the number of containers necessary to store a bunch of things given that they're arbitrary sized, and you want to minimize the amount of wasted space, basically, when you pack stuff. So this happens all the time. Tetris is a game of bin packing that happens in real time, and it's quite entertaining. Actually, Tetris is the most successful video game ever created because it has no language or cultural barriers. It's colorful but doesn't have complicated instructions. But it's a version of bin packing, and that's an NP-complete problem. There's also versions of Tetris that are made of plastic that are actually real artifacts, not just videos. Tetris also has shelving kind of Tetris-based shelves where you can rearrange these shelves. These are all the loose parts. You can rearrange them in arbitrary kind of Tetris-like positions to accommodate your stuff. So like this long shelf here can hold, say, a vertical wine bottle, but if you put it horizontally, it can hold a bunch of candles or whatever it is. So these are like polymorphic shelves. Makes a great Christmas gift if your loved ones are interested in bin packing and NP-completeness. Any questions so far? So I'm just giving you a lot of interesting, common real-life problems which were all shown to be NP-complete. Another one, the Steiner tree problem. Given a bunch of nodes, connect them with the least amount of total interconnect length, wires or whatever. So for 3 nodes, it's pretty obvious. You can connect them as a minimum spanning tree, and the cost will be 2 units. Or you can add 1 node in the middle, a new node in red, connect all 3 nodes to the middle, and you've saved some total interconnect length. Here, the total length in red is the square root of 3, 1.7, roughly. So you saved about 15% by going from the green to the red connection. But in general, it's not so obvious. If I give you 20, 30, 50 points, how would you figure out where to put the new red nodes to minimize the total interconnect length over the entire set of nodes? Not obvious at all. And these are just geometric versions. The graph version is even more general because costs can be arbitrary. The edge weights can be arbitrarily weighted, not necessarily just geometric distances imposed by the underlying metric. Yeah.
What's different from this and just solving the minimum spanning tree, which can't be done?
He's asking a very good question. Why can't you just apply some minimum spanning tree technique? And here we do. So this is the minimum spanning tree over these 3 nodes. But the minimum spanning tree, you cannot add new nodes. You're stuck with the nodes that you're given. You can only use nodes that were there as part of the input to your algorithm, namely those 3 nodes in blue. But if you're allowed to add brand new nodes, like this one in red, now you can save. So the difference is the ability to add new nodes that you were not given before. Yes, you can recalculate the minimum spanning tree with the new nodes, and the answer is exactly that. problem is, where do you put the new nodes? Where would you place them in the plane to minimize the total overall quantity? See, I gave you these 3 nodes and their coordinates, but I did not give you the red one. You had to calculate where you want to put the red one to minimize the overall minimum spanning tree over the blue plus the red. But it's up to you where you put the red ones, and there's a lot of leeway. In fact, in a continuous version, there's an infinite number of places you can put the red node. And you have to decide which one will be the best, because if you put the red node like way out here, it's not going to save you anything. In fact, it's going to cost you extra relative to this green. So you have to put it in a place that not only doesn't hurt, but actually helps. Not only helps, but helps the most possible from all the other places you could have put the red node. And it's up to you to decide. That's what makes it hard. It's like, where do you put those red nodes? Once you know where to put them, the rest is easy. Just run minimum spanning tree over the blue nodes plus the red points. And that's the answer, actually. So you can run Prim's algorithm or Kruskal's algorithm over the union of the 2 sets of nodes. So the question is so if I give you this blue points, it's not at all clear where to put these red nodes. But here I'm showing you a good place to put the red nodes so that the overall tree is minimized in length. And that's the hard part, where to put the extra nodes. These are called the Steiner nodes, the extra nodes that you add. And the graph version is even worse, because I say in this connected graph, I want a spanning tree that connects all the blue points to one another, a spanning tree over all the blue points. And the red points I don't care about, but you can use them optionally to reduce the overall length. So the red points are potential Steiner points. But the question is, which subset of the red nodes should you use so that Prim or Kruskal, minimum spanning tree, over the blue plus the reds that you choose is minimal? And that's not obvious at all. In this example, it's the red tree here. So this red tree uses all the blue ones. It spans all the blue ones, and it uses only a few of the red ones, and other red ones it does not use. And out of all the possible subsets of red ones, one of them will be the best, but you don't know which. And you can try all of them, sure, but there's an exponential number of subsets. So it makes the problem very, very difficult, actually. And there's been many books written on this problem. I'm just showing you my favorite top 5 or 6 books written on the Steiner tree problem. Heuristics, exact solutions that are highly optimized, still exponential time, but highly optimized exact solutions, and hundreds of different heuristics have been proposed for this problem over the years. And some of my own papers also did the same for this problem, proposed heuristics that are pretty good. I have a heuristic for the graph version of the problem, which is the most general version, because here the weights can be arbitrary weights, not just geometric distances. So I have a heuristic for the graph version of this problem that for over a decade has held the world's record for the best known theoretical bound for a polynomial time heuristic for this problem. Right? So, and it's not necessarily the best. It could be beaten one day. And this problem is very ubiquitous. So for example, if you want to connect all the lights in this entire building to each other and to the main transformer outside the building, you want to use the least amount of total electrical wiring in the walls to do that, because there'll be less labor and less parts and less electrician time and less conduits, and it'll minimize the cost. So that's exactly this problem in 3 dimensions, right, in this building. How many get that? And same if you want to connect all the air conditioning ducts in the building. That's another Steiner tree. And if you want to connect all the water faucets and toilets and sinks in this building to the main water main outside the building, again, that's a Steiner problem. Now you're using water pipes, not electrical conduits. So, every single building has multiple versions of this Steiner problem embedded in the walls, literally, when you construct a building. And by the way, the Steiner points in that scenario, what are they? Which points, which extra points do you use besides what you actually want to connect, which are all the lights and all the faucets?
For pipes, for example, like a T.
Yeah, for pipes you have like T intersections or cross intersections. These are the extra points, the junctures that you add where other things can connect to. Same for air conditioning conduits. There's these, main T sections or cross sections or other kind of connection points that you add, and those you can add at your leisure, at your convenience, at your discretion. Nobody's telling you where to put those. You can put those wherever you want. The other points you need to connect are fixed. The faucets are at certain fixed positions, but the T junctions, that's up to you. So that's the Steiner problem. Any questions about that? And there's literally hundreds of heuristics for each and every one of those problems. We're going to go through some possible heuristics for some of these problems. I don't know if we'll get to them today, but certainly by next time. So certainly heuristics are pretty obvious, right? So for example, for the Steiner problem, if you ask the problem, if you only add one extra point, and in the case of conduits, one T-section, you're only one T-section, you put that wherever you'd like. Where would you put it to minimize the overall length of the entire original point set plus the T-section, single one T-section that you're allowed to use? Not many, but one. That problem, turns out, you can solve in quadratic time. It's called the one Steiner problem. One Steiner point, no more. Now, if you're allowed to use one and you find the best one, and that you can do in quadratic time, polynomial time, you can iterate and find now a new point and a new point. Make that T-section one of your original points. Now you have n plus 1 points. And then ask the question again, where you put one more Steiner point to minimize your overall length again. And keep repeating. So you do this repeatedly. And if you do this repeatedly, the total interconnect cost, the minimum spanning tree cost over all the points so far, plus all the Steiner points so far, will keep dropping and dropping and dropping until you can't drop anymore. You'll reach some barrier where you can no longer save anymore. And that's a heuristic, an approximation algorithm for the Steiner tree. How many understand this heuristic? Pretty straightforward, right? It turns out that works pretty well. I invented this in the early 90s as part of my PhD, actually. As simple as it sounds, nobody thought about this before, 25 years ago. So then I ran it, implemented it, ran on thousands and thousands of point sets, took the average behavior, graphed it. It turns out it's only about 1.5% of optimal. And I also computed the optimal brute force way. It's point sets of size 5, 10, 15, 20 points, randomly selected, uniformly distributed in the unit square, and so on. So that heuristic, as simple as it sounds, and it is simple, will get you either optimal or very close to optimal, and on average will be 1/2% of the optimal cost. And that's pretty good. Of course, there's no guarantee it'll be the optimal always, because then P will be equal to NP, and then I'll probably get a Turing Award, not just a PhD for it. But the point is, heuristics are easy to come by. For example, traveling salesman. We all know traveling salesman is NP-complete, so how do you solve it heuristically? Well, start wherever you'd like and go to the nearest unvisited location. Then from there, go to the nearest remaining unvisited location. And from there, go to the nearest remaining unvisited location again, repeatedly. And when you do that, you'll get some sort of a tour. It won't necessarily be the optimal, but it'll be a pretty darn good tour. It's called the nearest neighbor heuristic for traveling salesmen. And that heuristic is actually used often when delivery people need to deliver packages to neighborhoods like FedEx or UPS or the post office. Or maintenance people need to visit a bunch of sites to fix, plumbers or electricians need to visit like a dozen or 2 dozen homes in one day to fix things. They usually go to the nearest one first and the nearest one after that, and it may not be the optimal, but it'll be pretty good. So heuristics are easy to construct, approximation schemes. And they better run in linear time or quadratic time at most. Anyway, fast, they gotta run fast, because you need to compute them every single day that you operate, whether you're a plumber or electrician or FedEx or UPS or any kind of deliveries. So these problems are all over the place and they need to be computed fast. We can't afford to wait a century of CPU time to compute the exact solution to deliver 50 packages, right? Just to save 2 miles of distance or half a gallon of fuel. So these problems need to be solved all the time, and we don't know how to solve them exactly because they're all NP-complete. So we always resort to heuristics once we know they're NP-complete. If we don't know the NP-complete, be careful not to jump to heuristic solutions unless you know the problem is intractable first. So for example, if I ask you to multiply numbers together to compute account balances in terms of accrued interest and so on for a financial institution, we'll say, okay, I'll have a heuristic for multiplication that approximately multiply. No, because that you can do it efficiently, quickly, and exactly. So you don't want a heuristic for a problem that's easy to solve exactly in polynomial time or linear time or efficiently in any case. So I hope that schema makes sense to you. Any questions about any of that? Okay. So if you know a problem is NP-complete, that gives you license to solve it approximately without risk of embarrassment that one day somebody will solve it exactly in quicker time, but you can solve it approximately, beating you both in time and in solution quality. Because if it's intractable, it ain't likely going to happen, basically. Okay, so speaking of traveling salesperson, that's the problem here defined formally. You have a bunch of destinations, and you want to minimize the total tour length through all these destinations. It happens all the time when you travel or are a tourist somewhere. You have a bunch of places you want to visit, and you don't want to spend too much time on the road. You want to spend more time looking at interesting destinations. So many books have been written about that. And Google Maps have an app that allows you to construct some minimum kind of traveling salesman solutions for a bunch of given destinations that you specify and so on. We also mentioned you could have TSP art that uses the TSP kind of heuristics to create art. Basically, it's a single tour through a bunch of points, but it looks like something as opposed to just be random points. So again, many heuristics. It's a ubiquitous problem. FedEx, UPS needs to compute these tours every single day. And when you go on vacation, either implicitly or explicitly, you're sort of computing tours of where to go to first and next and so on to maximize your leisure time or minimize your travel time or stuck in traffic time or whatever it is. Happens all the time. Some of my papers have proposed heuristics for traveling salesmen. In fact, I invented a whole new version of traveling salesman where the points can move. So these are fixed points. They're stationary, like cities on the map. But what if the points themselves can move, like planes in the sky or ships at sea, and you still have to visit them one at a time with a tour? So it's now more complex because now there's a time dimension and they move. So you no longer have to visit the point, you have to visit where the point will be when you actually get there, which is a different location from where the point is right now. Okay, so it's called traveling salesman, moving target traveling salesman, where the targets move. And now everything is more complicated because classical traveling salesman, as hard as it is, as NP-complete as it is already, is a special case of my version where here all the velocities are zero. And in my version, it could be arbitrary vectors of a direction and a velocity. And even if you consider it constant velocities, it's still very hard. I mean, even when the velocities are all zero, it's already NP-complete. So imagine how much harder it is when these points can move. Question?
You say the points move, are you assuming that you know how they're going to move and predict where they're going to be?
Yes, because if you don't know where they're going to move to, all is lost, right? Imagine trying to play tennis and you have no idea where the ball is going. It doesn't matter how skillful you are, it'll be a random game, right? And chances are, pretty boring game to watch. Right? You'll miss every shot, basically. So just like in tennis or in some sports, you can assume so that the points move in constant velocities in constant directions. In other words, every point has a vector associated with it. So the vector has a direction, and the magnitude of the vector is the velocity. So arbitrary velocities in arbitrary direction, but constant motion. So it doesn't just meander around in arbitrarily crazy, paths. So yeah, that's a constraint. Although you can allow more complicated paths as long as they're reasonably computable and predictable. So if you want parabolic paths, that's okay too. Or some other spline-looking kind of paths, just not random paths. Question? You mean the art? No, the map. So they probably use some sort of a nearest neighbor, then optimize with something called 2-opt. So once you have a nearest neighbor heuristic, some of the edges could be unnecessarily long. So then they look for edges to swap. So if you have edges that cross like this, you can swap them into another pair. In other words, you change the figure 8 by uncrossing the middle into an ellipse. And that could save you a little bit of travel, a few miles here, a few kilometers there, a few gallons of gas here. And then you keep doing this potential swaps. Now the swaps will eventually peter out and quiesce on some equilibrium that cannot be improved anymore with any more swaps. And that's when they stop. They could use, this is called the nearest heuristic plus a 2-opt optimization on top of that. Now, if the number of points is small enough, like in this example, they have about 10 points, right? 9 points. If the number of points is small enough, they probably use an exact solution. Because if you have, how many permutations of 9 points are there? Because a TSP tour, traveling salesman tour, is nothing but a permutation. How many get that? It's just some ordering of the points, which is just a permutation of the items. So if you have n items, how many permutations can you have? How many possible tours can you have? Not a trick question. N factorial. Now, n factorial grows pretty large. But for n is equal to 5 factorial is not so large, right? The factorials are, 1, 2, 6, times 4 is 24, times 5 is 120, times 6 is less than 1,000. So if you have 5 points, there's only 1,000, less than 1,000 different permutations. And that's, you can go through them very quickly in a few milliseconds on a computer. Now, if you have 10 points, it'll be millions, but still only a few seconds on a computer. So Google could do that for you, say 9, 10 points. But if you get to 20 points, 20 factorial cannot be done easily. 20 factorial is so many trillions that ain't going to happen in seconds or even minutes of CPU. It'll probably take days of CPU time. And that's just not going to happen. So again, that's typical of NP-complete problems. The problem is small enough, you kind of eyeball it, look at brute force, all combinations, even satisfiability, which we know is NP-complete, Cook's theorem. If the formula only has 10 variables, how many combinations do you have to go through to solve it brute force and look at all possibilities? About 1,024, I 2 to the 10. And 1,024 different possible, Boolean variable assignments, you can go through it in just milliseconds. It won't even be seconds of CPU time, right? Or even microseconds in this case, because it's only 1,000. But you get to 20, there'll be 1,000,000. If you get to 30, there'll be 1,000,000,000. 2 to the 30 is 1,000,000,000 roughly. Now we're talking, real time here, not just microseconds or milliseconds. If you get to 40, it's kind of hopeless already. So every problem has its own threshold where it becomes infeasible to solve with brute force, right? And you have to figure out what the threshold is and do the right thing. And one algorithm doesn't exclude the other. Just because you use a nearest neighbor heuristic for traveling salesman doesn't mean you can't solve small problems in brute force exact manner. And you can. That's part of your meta heuristic now. Look at the problem size, and based on that, decide which subroutine you want to call it, exact solution or heuristic solution of one kind or another. Or you can have a big case statement, kind of, making that decision up front before you start. What else? Yeah. So he's asking a good question. Is my version of moving target traveling salesman NP-complete? Or is it harder? Well, it's at least NP-complete because this is a special case of my version. It turns out it's not any harder in a theoretical sense. And that's a very good question. So how many understand this question? He's saying maybe it's even harder than NP-complete. Why isn't it harder than NP-complete? Or let's put it that way. Why will an exponential time, brute force, factorial time algorithm still work for this version where the points are moving? How many say, yeah, exponential time? Yeah, it will work. Look at all permutations. My tour for a moving target traveling salesman will still be a permutation at the end. That's all a tour is a permutation. Which you go first, which you go next, which you go next after that. Of course, it's a little bit trickier to compute what point you will go to meet the moving point once you get there. It's like Wayne Gretzky, the great hockey player. How many heard of Wayne Gretzky? Am I dating myself? Okay, good. So legends never die, I guess. When they ask him, how come you're so good at hockey? He says, it's simple. You don't go to where the puck is. You go to where the puck will be when you get there, right? You ever heard that expression? And of course, that's a kind of simple way of explaining why you're so good at tennis or hockey or soccer for that matter. You don't go to where the ball is now. You go to where it will be when you intercept the ball. That's hard to compute. So in moving target TSP, you go to where the point will be when you get there. But it's still the next point. And the thing is still a permutation at the end. So brute force, going through all permutations, will get you there. And because the moving target TSP is a generalization of this, or more precisely, this is a special case of moving target TSP where all the vectors are 0. It's NP-complete because if all of NP reduces to this, certainly it reduces to my version where all the vectors are 0. So it's NP-complete, and it's also in NP. right? Because if you want to ask, which is the shortest tour, you can guess a tour and then make sure there's no shorter tour than that. But anyway, long answer, yeah, it's NP-complete. But in practice, it's harder than this one because of the complication of the velocities. In fact, in regular TSP, traveling salesman, the tour cannot self-intersect. That's a theorem. You can prove that the tour cannot self-intersect. If it self-intersects, it's not the optimal tour, assuming the velocities are all zero. We're talking about classical TSP now. For moving target TSP, the tour can intersect. The optimal tour can intersect itself. So that's one more added complication. And by the way, let's prove this theorem, since it's so easy to prove that in the optimal TSP, classical TSP, the optimal tour cannot self-intersect. So if you have a bunch of points, right? I won't draw them all, but let's say the tour does this, right? And here's that pair of points where these two arcs intersect, and there's a whole bunch of other points. I won't draw them all, thousands of points. But for this pair of edges, there's an intersection. Prove to me that it's a cheaper tour than this. Yeah.
So if you think of like the x in the middle as like a square, flip it, and you do the two distances.
Yeah, so if you take these two edges here, and you replace them by, replace these two edges by these two edges, keep the rest of the tour intact, and this modified tour with these inside edges removed and these two outside edges added will be shorter than the original tour, so the original tour could not have been the optimal shortest tour. How many can see that? In 2 words, what's the reason for that? 2 words. You want to buy a vowel? Pythagorean theorem? It's close. What else? It's on the right track. Anybody? Be brave, say something. Nearest neighbor? Okay. What do you say? Cosine less than 1? Okay. So these are not wrong, but triangle inequality. How many heard of the triangle inequality? What does that mean? What does he mean by triangle inequality? That's right. Triangle inequality means? The triangle inequality basically means the shortest distance between 2 points is a straight line. It's not through a third point. Another way of saying it, the hypotenuse, one side of the triangle, is always shorter than the other two added together, which probably happens with some sine and cosine constraints, but you don't have to go that far to even mention sines and cosines, although technically you could. So one side of the triangle is shorter than the other two added together. So what does that mean here? This edge here is shorter than these two because there's a triangle here. And it doesn't have to be a right triangle, so Pythagorean theorem is not quite, because this triangle may not be a right triangle. But this dotted edge here is longer than these two. Shorter than the sum of these two. How many understand that? That's a triangle. Same here. This dotted line is shorter than these two. So these two dotted lines are shorter than these two edges in the middle. How many see it now? Good. And that's why a self-intersecting tour can never be the best tour, can never be the shortest tour, by the triangle inequality. So classical TSP, there are no self-intersections. So if you have a heuristic, like maybe the Google Maps app, that gives you a tour and has a few self-intersections, you know it ain't optimal. So one optimization, post-optimization after that is try to get rid of the self-intersections by replacing them with other pairs that reduce the cost even more. And that's called a 2-opt. That's what 2-opt does, that I mentioned earlier. 2-opt finds a self-intersection, there's 2 edges, and replaces it by another 2 edges that are shorter than that. And it keeps reducing the cost. And then there could be more self-intersections remaining, and you keep doing this repeatedly until there's no more self-intersections. Then you stop and output that tour. And that tour usually is pretty good. It's not necessarily guaranteed to be optimal. But it's a lot better than leaving the self-intersections there, which are obviously not optimal by this reasoning. Okay, any other questions about this? So heuristics are very straightforward to come by. That's why there's entire books listing hundreds of different heuristics. Yeah.
Is there an analog in your version of the traveling salesman problem, even though you have moving points, something you can detect to say, okay, well, if this exists here, then this is the optimal path?
Yeah. So he's asking, is there some sort of a two-opt heuristic, kind of way to detect non-optimality and kind of fix it one step at a time like this in the moving target TSP where the velocities are not all zero? Short answer, yeah. Except instead of looking at intersections, look at arbitrary pairs. So forget the intersection part. Just look at a pair of edges and ask yourself, does replacing this pair with these two pairs improve or disimprove the overall length of the tour? And if the answer is it will improve, obviously keep it. Repeat. So yeah, you can definitely do that for any version of TSP. Remember, it's just a permutation. So anytime you tweak a permutation, you can examine whether that tweak was an improvement or disimprovement. If it's an improvement, keep it and keep going. If it's a disimprovement, don't do that. Try something else instead.
But you do have to check. It's not, you can't take it for granted that it's going to actually.
That's right. You do have to check. Yes. Because in moving target TSP, you can have self-intersections in the optimal tour. So since you're so interested in moving target TSP, let me give you one more result that we had. It's another counterintuitive result. Let's say you're solving this problem, TSP, in one dimension. All the points are on a line. Think about what it looks like. So it's a great simplification because now it's one dimensional. So classical TSP, in one dimension, all the points are laying on the same line, like they're all on the x-axis. What's the optimal tour through all the points when they're all laying on the x-axis? Exactly, it's like that. Just pick them all up in order and go back to the beginning. Very straightforward. And that's the optimal tour. How many see that? There's no two ways about it. For moving target TSP in one dimension, where all the points are on the x-axis, but now they can move, that's no longer the optimal solution necessarily. It may be, but it may be not. How many can see that? Give me an example where it ain't. Yeah. Imagine you're at the origin right now, and there's a point there, so you start at the origin where that point is. And you have 2 points on either side of you. 2 points on either side. You were tempted to pick up the 2 points on one side and go back, pick up the 2 points on the other side, but no, because here's what can happen. These 2 points are on either side of you. The point that is the closest to you here and the point that's closest to you here are moving at a great speed away from you. The 2 other points are almost stationary. They're crawling. They're not moving very fast at all. These 2 points are moving away from you at the speed of light, just to be dramatic. So you don't want to pick up this point and the other point that's crawling and then go back and pick up these 2 points on the other side. You want to pick up one point that's moving at the speed of light and then backtrack and pick up the other point on the other side that's moving at the speed of light and then pick up the other 2 slow points, however many slow points they are. How many can see that? So the optimal solution will zigzag across the origin possibly many times, not even just twice. It won't be just pick them all up in a row anymore. So even TSP, moving target TSP in one dimension is actually not trivial at all. And by the way, we have an optimal solution for TSP in one dimension, polynomial time, because it's based on dynamic programming. It's a very restricted version. So as tricky as it is, one dimension could be solved optimally. 2 dimensions, forget about it. That's harder than regular classical TSP. That's some of the results we obtained. Lots of questions. I don't want to spend the entire period talking about TSP, but if you have questions, let's take it. Yeah.
So are we assuming you can move at any arbitrary speed?
Yes. Yeah, you can move at the speed of 0, which is what this is, or at the speed of light, or even higher speeds, because we're not bound by physics, right? So you can move at, warp 12, whatever that means. Is it 144 times the speed of light? Yeah. Any trekkers in the audience? You can move at arbitrary speeds. Yeah. All right. More questions? Yeah.
So would you say that like any enhancement to an NP problem is still NP complete, kind of like how the turn machine is like
Yeah.
enhancement
Good question. So he's asking insightfully, does any generalization to an NP-complete problem keep it NP-complete or possibly make it even harder than NP-complete? So yes, generally that's true. If you have a problem that's NP-complete, that's a special case of another problem, you better believe the other problem is at least as hard as the problem that's NP-complete that you have in your hands if the other one is a generalization of it, sure. Now, whether it's the same complexity or higher complexity, that can vary, right? So think about a Turing machine as a generalization of a finite automata, like you alluded to. So a Turing machine is at least as complicated as a finite automata, and it can recognize at least all the languages recognizable by a finite automata, but perhaps more. And in the case of a Turing machine, that's certainly true. It can recognize more than finite automatas can. But it for sure won't recognize less if a finite automata is a special case of a Turing machine. So yeah, in general, it's monotonic. The complexity, the superpower of a computation model, or the degree of difficulty of computing some function will only increase with more and more generalization up there.
So for a lot of these problems, we've been saying basically that you can brute force it in exponential time, and therefore you can do it non-deterministically in polynomial time. How strong is that of an argument? So if you encounter something that can be done in exponential time, how likely is it that you can then also do it in non-deterministic polynomial time?
It's sometimes not true. So he's asking, again, an insightful question. So he's saying, if you can do it brute force in exponential time, does that automatically mean that you can do it in non-deterministic polynomial time? Maybe and maybe not, depends on the problem. So for everything in NP, that's true. In fact, because simply NP is defined as a class of problems solvable in polynomial time non-deterministically. For P space, that may not be true. There could be problems in P space. All of P space could be solved in exponential time. Remember the Venn diagram, there was a Chomsky hierarchy. P space is inside exponential space, or exponential time, in fact. So everything in P space can be done in exponential time. But it's not clear that everything in P space can be done in non-deterministic polynomial time. If it could, P space and NP will be equal to each other, because NP is certainly in P space. That's an open question, whether P space is equal to NP. If P space is equal to NP, though, NP will not be equal to P as a corollary. So it's even, that question is even harder than the P is equal to NP question, because that will follow a simple corollary from that. So very good question. So it's not necessarily the case. Although it could happen, because remember, all of NP is inside P space. So if you happen to pick a problem that's in NP, but also and automatically it's already in P space, that will be true. And some other problems in P space, it may also be true about, even though they're not in NP, but others it may not be true about. Because P space is a pretty vast category containing NP and potentially many other things, although they could be equal. We don't know. These are all open questions. There's hundreds of open questions like that, not just P is equal to NP. Right? We listed a bunch of them a few lectures ago, right? Any other questions? All right, so that's traveling salesman. Here's a traveling presidential candidate tour of all the towns in the United States that happen to have more than a couple thousand people in them. So if you really want to shake hands, as a presidential candidate with, or any other political candidate, not just presidential, maybe congressional candidate, Senate candidate, if you want to travel everywhere in the United States, that's a traveling salesman tour over all the U.S. cities that are larger than a certain size. You have to make it larger than a certain size, because if you look at cities that have only 5 people, and I'm sure there's some towns that have only 5 or 10 or 50 people, it'll be a lot more dense than this. But generally, it's hard to compute, right? And you even have TSP humor and TSP cartoons and so on. Any other thoughts about TSP or questions or anything in general? Yeah.
Doesn't it require having global knowledge of the entire graph? What if each node only knows the weight of the nodes next to them, and doesn't know what beyond that? Then would that change the complexity?
Oh, he's asking if every node knows the weight of only its neighboring nodes and not other nodes. It's in TSP, you have complete knowledge of all the weights a priori and all the positions of all the nodes. So not only do you know your neighbors' weights in terms of distances to them, edges to your neighbors, but you know all the weights. And that still doesn't save you from complexity and intractability. If you have like a real-time version of TSP where you only find out the weights from a node to its neighbors when you get to that node, but not before, now it's even trickier. But now you're talking about a real-time kind of blind TSP tour, where you only go somewhere, show up, and then you look around and see your neighbors and then decide in real time where to go next, but you didn't know that ahead of time. So now you have to make decisions based on partial information, not complete information. Here we're assuming in every case complete information, even from moving target TSP. You have complete information of all the motions and all the positions, the vectors and distances to nodes and among nodes and so on. And it's still very difficult. If you didn't know those, it'll be even worse. Yeah.
So you mentioned a few times now that generalization will get you something that's as difficult or more difficult than what we were looking at in the first case. How do you match that against what Koya says and how to solve it about how sometimes generalization is a problem-solving strategy to get you an answer faster?
So another very good question. So he's saying if generalizing a problem does not reduce its complexity, but rather makes it worse, or if you're lucky, keeps it the same, why is it a good problem-solving strategy, like in Polya's book, to say generalize a problem and solve the generalization? So here we're not talking about complexity, we're talking about proofs and problem-solving techniques. And sometimes when you generalize a problem, the fluff goes away. So for example, let's say we considered the traveling salesman problem, but we said, let's couch it in much more specific terms. Let's say you have a FedEx truck with packages on them and delivery within 50-mile radius, and the packages have to go to particular homes, so it's not arbitrary locations, it's only where the homes are, and homes have GPS coordinates. I'm adding fluff now, unnecessary details that don't really capture the problem, they just obfuscate the general nature of the problem. So instead of talking about FedEx and packages and homes and deliveries within a city, why not abstract the problem? Instead of homes, talk about XY coordinates of positions. Instead of talking about FedEx and packages, let's talk about permutation of the points. And now, yes, it's a generalization, and we're not bound by a city or packages or homes or trucks, but now we can do away with the fluff and the red herrings and the unnecessary details, and we can see the crux of the problem more clearly, the essence, the spirit of the problem more clearly, and now we have many more insights. All of science has a long history of doing that. Generalizing, and the generalization is clearer than the specifics. Right? The Greeks had a model of the universe. It involved hundreds of deities and Zeus on Mount Olympus, and when Zeus would be sad, it would rain in tears, and if Zeus was angry, it would thunder, and all sorts of hundreds of different relationships among the deities, and very, very complicated, specific model, mired in all these minutiae and details. Then we decided to generalize the problem. What if it's only a few basic particles like neutrons and protons and electrons and only 4 different forces, and only really 2 of them matter, gravity and electromagnetism. The other 2 don't even matter very much. Now we have a few moving parts and very general description. That turned out to be much easier to solve, get a handle on, understand the world around us, and predict phenomena, right? And that's how the periodic table was created, from a few known principles, generalized, and that's how the Steiner model of physics was created. So in that sense, generalization, yes, it's a generalization, but it's simpler than the more specific, hairy, detailed problem that has a lot of minutia and unnecessary detail and red herring that obfuscate what's going on, not illuminate what's going on. So all of science is in the business of doing exactly that, and we've been doing it for 2,000 years, and it's been working out pretty good. Without that general strategy, we would not have iPhones or computers, for that matter. We'd still be inventing, new deities and all sorts of complicated relationships and involving jealousies and affairs, and also, and it makes for nice mythology. It doesn't make for great science. It doesn't make for iPhones and computers very easily. So that's how generalization helps in that sense. It doesn't hurt, usually. Sometimes it does make things more complicated. Right? General relativity is a lot more complicated than special relativity, because now things can move with arbitrary positions, arbitrary velocities and accelerations. But that helps explain more things. So you get more bang for your buck when you generalize. Good question. Anything else for now? Okay. So that's traveling salesman. Graph colorability, we'll talk a lot about this problem. So I give you a graph and adjacent nodes must have different colors, and the question is, can it be colored, colorized with, say, 3 colors or 4 colors, k colors for a given k. So here's this graph colorized with 3 colors. Can this graph be colorized with only 2 colors? This graph here, using only 2 colors where no 2 adjacent nodes share the same color? How many say no? Good, why not? Give me an argument.
It has a complete subgraph of size 3.
Yeah, it has a subgraph of size 3, a complete subgraph, a triangle in other words. And a triangle, you need 3 colors because everything's connected to everything else. So 2 colors will not suffice. So in general, that's a hard problem. This graph here, I'm 3 coloring it. And you can look at all possibilities, all the different color possibilities, but there's an exponential number of them usually. Every node can be represented, colorized with 3 different colors, say. So there's 3 to the n different possible ways of colorizing n nodes. Then you check for each one if it doesn't break the color constraints that no 2 adjacent nodes share the same color. And yeah, you can do it brute force, but that's exponential time. And nobody knows in the polynomial time algorithm, and we know it's NP-complete. In fact, we're about to prove it's NP-complete. I don't know if we'll get to this today, but it is. So these are some of the problems, and there's hundreds of others. And those particular problems I just showed you all come from a famous paper by Richard Karp from Berkeley, and this is 1972 on the heels of Cook's paper. He showed that not only, like Cook said, satisfiability has this amazing property that it's as hard as anything in NP. Everything in NP reduces to it in polynomial time. But he says a bunch of other problems have the exact same properties. Nothing special about satisfiability in that respect. And that opened the floodgate doors to NP-completeness. And it showed us that not only satisfiability is NP-complete, not only these set of 20 problems or so is NP-complete that Karp lists in this very paper, but literally there's hundreds of problems and even thousands of problems that we have to solve every single day in our lives that are all NP-complete, all have this property. And so it's a ubiquitous general phenomena. It's not just an esoteric onesies and twosies and happens here and there. It happens almost everywhere. The problem of scheduling classes, turns out it's NP-complete in the general case. So now when you have trouble finding classes in the schedule of classes and you can't make all the times fit and against all the requirements for a graduating degree, now you know why. You're solving the NP-complete problem. And so how do you solve it? Well, heuristically, you try different things. If it doesn't work, try something else. If it doesn't work, or you can try all possibilities of all the possible classes you need to graduate, all possible subsets of them, respecting the prerequisite requirements, of course, and so on. And you can do it that way, brute force. But that's an exponential number, usually. And usually you don't have exponential time to construct your schedule. I assume you don't. I don't. I didn't when I was a student. Okay, so anyway, Karp's paper, single authored. It's on the reading list for extra credit. Go through it and tell me what you know. But look, he says right out of the gate, very affirmatively, very intentionally, explicitly, he says, we show that a large number of classic unsolved problems of covering, matching, packing, routing, assignment, sequencing are equivalent in the sense that either each of them possess a polynomial time algorithm or none of them do. In other words, they're NP-complete. All of NP reduces to each one of these problems they list in this paper. And he gives Cook a lot of credit. Look, it says this paper was stimulated by the work of Stephen Cook, 1971, which is a year earlier from this paper, which is 1972, and rests on an important theorem which appears in his paper. He gives him a lot of credit for laying the foundation upon which this is building, and this ushered in all of NP-completeness on the back of Cook's theorem. Then he talks about the class P, polynomial time, deterministic polynomial time, the class that we know and love. And by the way, this is the entire, I'm showing you the entire paper. This paper is so important that at least once in your life you should see the entire paper, and there it is. So it talks about deterministic algorithms, right? It talks about problem solvable polynomial time. It talks about reducibilities here, which is that diagram we keep showing for A reduces to B through some function F. So it talks about that over here. Next couple of pages, right? It talks about sampling of problems, satisfiability, with at most 2 literals per clause. That's 2SAT. Remember we said 2SAT is solvable in polynomial time for extra credit. Prove that. There's 2SAT. It talks about minimum spanning trees. Now it goes through some polynomial time deterministically solvable problems. Spanning tree, you can do it using Kruskal or using Prim. You all know that because you've seen that in algorithms. Shortest paths problems, that's Dijkstra's algorithm, 1959. more polynomial time deterministic solvable problems like bipartite matching, linear equations, and so on. And now he starts talking about non-deterministic algorithms and problems solvable in non-deterministic polynomial time. And again, Cook's theorem is mentioned here very explicitly. Again, it says in this section we state an important theorem due to Cook, which asserts that any language in a certain wide class NP is reducible to blah, blah, blah. And we already covered that. Cook's theorem and reducibility of all of NP to satisfiability. And it talks about non-deterministic one-tape Turing machines and how all of NP reduces to it, and satisfiability is NP complete. And again, he credits Cook multiple times, which is nice. And then satisfiability is NP complete. And now he goes and starts proving lots and lots of other problems are NP complete, not just satisfiability. And he gives a long list. So here's satisfiability, the first one, right? And here are a whole bunch of others. Clique, we already mentioned, right? Packing, bin packing, we mentioned. Let's see, Hamiltonian cycles, right there, we mentioned that, right? And there's a bunch of others. Number 11 is satisfiability with most 3 literals per clause. That's 3-sat. We proved 3-sat is NP complete. I remember that. So last time and this time too. And he proves it over here, or he lists it and then proves it. Clique, we mentioned that. Chromatic number, that's graph coloring. We talked about that, painting graphs with colors. Steiner tree, I mentioned that. I worked on that. Matching problems, knapsack, we mentioned that. Collecting stuff when your house is burning or when you get on a plane, you reduce your luggage to under 50 pounds or whatever. That's that problem right there, knapsack. And a bunch of others. So he calls these complete problems. Now we call them NP-complete. Remember, this is the first time this term was ever mentioned in a paper, or by anybody for that matter. So terms sometimes evolve. But that's the origin of NP-completeness right there on this page of this paper in 1972. And the entire theory is built on that. So just a monumental paper. So here he reduces satisfiability to clique. So now he gives proofs of the NP-completeness of each and every one of these problems on this list of 21 problems. And some proofs are easy, some are a little trickier, but the rest of the paper is just proof after proof after proof. And we already saw proof from one of them, right? Satisfiability, 3-sat. So we already seen a proof for this one, number 11. We'll see proofs for a few others before we're done. Yeah?
Is Sudoku a graph coloring problem?
What's graph coloring?
Sudoku.
Oh, Sudoku. Sudoku, how is it pronounced? Sudoku. Is that a graph coloring problem? Well, generalized Sudoku is probably NP-complete. I wouldn't be surprised if it is, although I'm not sure. Somebody must have either proved or disproved it, one way or the other. And because of all these reductions, and everything in NP could be reduced to everything in NP in polynomial time, to everything else in NP in polynomial time. If Sudoku is NP-complete, I guess you can say it's a graph coloring problem because you can reduce it to graph coloring and then solve the graph coloring problem. So modular transformation, there all are problems like all the other problems. So for example, if you say, is satisfiability a graph colorability problem? Well, with the right transformation, it is. That's the whole point of these transformations. I hope I didn't confuse more than illuminated that issue. Yeah. Okay, so you just confirmed Google search. Thank you, Sergey Brin and Larry Page. That Sudoku is NP-complete. So yeah, in a sense, it is a graph colorability problem. It's also a satisfiability problem. It's also a Steiner tree problem. It's also a traveling salesman problem, given the right reductions. So if you had an oracle for any one of them that was running in polynomial time, you'd have an oracle, an algorithm for all the other ones using the oracle as a subroutine. Yeah. Now, let me say something, since you mentioned Sudoku. So Sudoku usually is a 3 by 3 by 3 by 3, right? There's like a 3 by 3 grid of 3 by 3 subsquares, right? If I'm not mistaken, is that how it works? Okay. So the point is, it's of size 3, or 3 to the 4th, or whatever. Now, that problem by itself is not NP-complete simply because it's of size 3. So there's only so many integers you can fit in a 3 by 3 by 3 by 3 grid arrangement. And yeah, it's a big number, it's exponential, but if 3 is fixed, so is the double exponential in 3, or however many there So you have to have generalized Sudoku for it to be NP-complete. Now, it's easy to generalize Sudoku. Instead of having 3 by 3, just have 4 by 4 and have 16 of those 4 by 4 grids, or 5 by 5 and have 25 of those 5 by 5 grids, and so on and so on. Once you do that, now you have an NP-complete problem, but you have to generalize it. Simply because NP-completeness is not about one problem. It's about a class of problems, a class of instances of that one problem, just like the halting problem, right? So if I say, the Unix operating system, is it decidable whether it ever halts or doesn't on its own? How many say it's decidable whether the Unix operating system halts on its own? How many say it's not decidable? Well, I'm glad I'm asked because I'm seeing a split vote. So this is a very important point. Let's harp on this for a minute or two. It's worth it. Consider the language made up of the string yes, just the one string yes, if the stock market will be up tomorrow from today's close. Consider this, the language or it's equal to no, the single string no, if the stock market will be down tomorrow from today's close. How many say that's a decidable language? How many say it's not decidable? How many say it's a regular language? How many say it's not regular? Good, you got that one. It is decidable, it is regular, simply because it's a single string and there's a machine that accepts it. We don't know which this machine is today, we will know tomorrow, but the machine still exists today as it will tomorrow. Just because we don't know what something is doesn't will it out of existence. The flip side of that is an insidious point of life. Just because you are able to speak of something doesn't will it into existence, just because you utter those words. Some people could learn that lesson in life. So, traditional Sudoku, 3 by 3, is nothing NP-complete about it. But if you generalize it to arbitrary size, now it becomes NP-complete. And that's a general trend. No single instance is very complicated because a very simple algorithm that decides it. Yes, an algorithm says yes or an algorithm says no, and that's the end of it. Even if it's a finite number, however large, there's still a big case statement algorithm that decides all those finite instances, and that too is not undecidable and not NP-complete. It's solvable in constant time. If there's only a constant number of instances, however large. Make sure you wrap your mind very tightly around that concept. Otherwise, you'll be confused about a great many other things. Follow up. Yeah.
So basically, to clarify, for something to be NP-complete, it has to be a class of problems that has an infinite number of possibilities.
Yes. It has to be infinite number of instances. Why? Because if it's a finite number of instances, there's one big constant time algorithm that solves the entire class of finite number of instances, one giant case statement. One answer for each instance. Yeah, it'll be a very long, big case statement, only one case statement, which will take constant time to run. How many get this? Good, it's very important. It was worth 5 minutes of harping on this subtle point. Okay, back to this paper. So the rest of the paper basically proves that all these problems are NP-complete. And here's a schema of all these proofs. Here are all the problems, all 21 problems that he lists. And these arcs, these edges in this tree are proof reductions. So he reduces satisfiability to 3 sat. So this arc corresponds to a proof that we already proved a few slides ago. How many get that? And here are all the other arcs representing the other proofs for the rest of the paper. So this shows you a roadmap of what was reduced to what in this paper. Now, we didn't have to do it in this sequence. This is just the sequence that this paper happened to be written against as this roadmap of proving things by reductions from other things goes. And this is the schema he uses. So he reduces then satisfiability. He reduces 3 sat to graph colorability. Then he reduces graph colorability to clique cover and also separately to exact cover and so on and so on. So to reduce satisfiability to, say, partition right here, he has to go through this reduction, this reduction, this reduction, this reduction, and that reduction, all these 5 reductions composed together, one on top of the other, until you get one giant reduction that's the composition of these 5 other reductions. But because each reduction is polynomial time, polynomials compose into yielding other polynomials of higher degree, yes, but polynomials nevertheless. as the composition result. So how many see what's going on here, what this represents? Okay, any questions about this? Yeah.
Does that mean if you have a heuristic algorithm that can solve one efficiently, does that mean you can then use that to solve like satisfiability or something?
If you have an algorithm to solve one of those efficiently, all the others will be solvable efficiently too.
So then the algorithm you created, could you use that to solve satisfiability as well?
Oh, you mean the algorithm that I created personally? Okay. That's a very subtle question. So let me try to explain it as simply as I can. These reductions preserve exact solutions. They preserve set membership to set membership. Members map to members and non-members map to non-members. So yeses map to yeses and nos map to nos. But what it doesn't do, these transformations, it doesn't map almosts to almosts. It doesn't map close enough to close call over here. You can have a very close call here that'll map to something that's outrageously out of bounds over there, and vice versa. So it doesn't preserve approximations. It preserves exact yeses and nos as set memberships. So yeses map to yeses and nos map to nos. But cheap doesn't map to cheap and expensive doesn't map to expensive. Not at all. It could be quite the opposite. It could map approximations to other approximations on the other side of the fence if you're very lucky, but luck is not a very good algorithm to make, to base your fame and fortune on. So approximability is not preserved. Now, having said that, there's a whole new class of reductions and transformations that does preserve approximability, but those are much more difficult and hard to work with and esoteric kind of reductions than the ones we've been seeing. And the ones we've been seeing are difficult enough. So you don't have to worry about that, but they're out there, and there's a whole class of study of complexity and transformations of problems into one another that preserve approximability or the goodness of solutions. So good solutions will map to good solutions here. Bad ones will map to bad ones. But these transformations just map yeses to yeses and nos to nos. They map solutions to solutions and non-solutions to non-solutions. But it doesn't map close calls here to close calls there. So be careful about that. But it's a very good question, because if that was true, a good heuristic for one problem will automatically provide a good heuristic for all the other problems. It's just not true. In fact, in general, it can't be true. You can show that can never happen in general. Why? Because there are NP-complete problems that can be approximated arbitrarily close to optimal in polynomial time. We can show that. Traveling salesman is actually one of them. On the other hand, there are problems in NP, there are problems in NP-complete that cannot be approximated to within arbitrarily close to optimal, provably so. In fact, there are no general arbitrarily close to optimal approximations to many NP-complete problems. Some problems are just not approximable. They're all solvable in non-deterministic polynomial time, yes. They're all NP-complete, yes. But with respect to approximability, some are approximable and some ain't. And you can prove that, actually. So you can't generally have an approximability preserving transformation simply because of that. They're all transformable to one another, but some are approximable, some aren't. I hope that sheds some light on that. But it's a very important question, actually, and it's a subtle issue. More questions? Okay. So that's how he proved all these things. And then he goes through and proves it. Here's the satisfiability reduces the satisfiability to 3 sat. So here's general sat reduces to 3 sat. Remember, you had this long Boolean formula here, and here you introduce all these other variables, which I painted green, blue, and red, and so on, these conjunctive variables. And so from this one big clause of variables, you create a bunch of little clauses, each one having at most 3. How many remember that in my slides? So there it is in the original paper. Of course, when you use colors and nice big fonts, it's clearer, but there it is right there. And there's a bunch of proofs for all the other transformations as well. So again, he talks about there a bunch of more times, and here it talks about p-space complete problems, although p-space completeness wasn't invented yet. Remember, this is the invention of NP-completeness, and other completeness theories followed on the heels of that. But regular expression equivalence, whether 2 regular expressions that I give you are the same or not the same, that's p-space complete. It's worse than NP-complete. Whether 2 non-deterministic finite automata are the same, that's p-space complete, worse than NP-complete. And context-sensitive recognition, we still don't know to this day if it's an NP or not an NP. And other problems that he mentions, interestingly, graph isomorphism, we talked about it last time, it's still open whether that's NP or not, although there's a pseudopolynomial algorithm for that. And primality testing, at the time that this paper was written, 1972, it was open whether it's in P or not. Now we know it's in P. We use, so here, but it does say, that the following important problems are in NP, but they are not known to be complete, not known to be NP complete. And now we know why primality testing is not NP complete, or because it's solvable in polynomial time. And that's a very recent result. It was only 30 plus years later after this 1972 paper was written. Next time we'll talk about more transformations. We're about to release the next homework. The next homework will be, or the next homework assignment will be the last of the semester. You'll have a couple of weeks to do it. It'll be released in a couple of days, this weekend at the latest. And then we'll have the midterm. Last class will be May 1st, Tuesday. The midterm will be released very shortly after that, maybe that same day. You'll have a week to do that. That'll be the end of it. So at some point soon, I'll schedule a Tesla Model S demo day. We'll bring in the Luck Dragon, which is what my license plate is. And we'll have tours around the block. I get to drive, not you, insurance reasons. And it'll be fun. How many interested in the demo, just to get an idea of, okay, well, we'll schedule a time block that accommodates all of that. So I'll send an email about that. All right, so we'll see you next week.